Hey everyone, my name is Lyndon Hillenbrand. We're coming to you from Cloudera HQ, and today we're going to talk about thinking about big data and thinking at scale. So we're going to cover what are the characteristics of large-scale computations, the pitfalls of distributed systems, and how do you design for scalability. So let's take a look at the numbers. So the max data in memory that you can hold is actually 256 gigs. The max data per computer is about 24 terabytes. The data processed by Google every month is 400 petabytes. That was in 2007, 4 years ago. You can imagine what it is today. The average job size is about 180 gigs. And time that it would take to read sequentially off a single drive is 30 minutes. So, what does this mean? This means you can process data very quickly, but we read-write it very slowly. So the solution, we need parallel reads. So one hard drive operates at about 100 megs per second. That's seek time. If you had 1,000, that's 100 gigs per second. Now we're talking. So traditional distributed computing. If we look at sharing, data is stored on a small number of storage area networks. At compute time, data is copied to compute nodes. This means you're copying data back and forth. As your data sizes grow, this just isn't an efficient solution. There's network constraints, network bandwidth, as well as disk seek times that just cause major constraints on the design scale. Like I was just saying, sharing is slow. If you have grid focus, that's distribute the workload. So you have SAN drives and many compute nodes. But the modern focus is to distribute the data. Reading 100 gigs off a single file will leave nodes starved. Just store data on the local disks. Sharing is tricky. So exchanging data requires synchronization. Deadlock becomes a major issue. Finite bandwidth is available. Distributed systems can literally drown themselves. Failovers cause cascading failure. Temporal dependencies are complicated. You really need a system that can linearly scale, and if it fails, it's fault tolerant, where it's failing linearly. So how do you handle failures? Well, there's a quote by Ken Arnold, a Corba designer, and he said, "Failure is the defining difference between distributed and local computing." We really need to rethink distributed computing. What reliability demands do we have, given the pain points from sharing and given the failure as a defining point? So, how do we support partial failure? The total system must support graceful decline in application performance rather than a full halt. So if you take, for example, you're running 1,000 commodity machines, one is bound to fail. 1 out of 1,000, if that breaks the system, that's a major design flaw. We need data recoverability. If components fail, their workload must be picked up by still functioning units. And individual recoverability. If a node fails, it must be able to start and rejoin the group activity without a full restart. Consistency. So concurrent operations or partial internal failures should not cause visible non-determinism within the system. And scalability. So adding an increased load to a system should not cause outright failure, but graceful decline. Also, increasing resources should support a proportional increase in load capacity. So if I have 50 nodes in my cluster and I had 50 more, technically my performance time should increase double. So what are the motivations for MapReduce? Well, we're looking at data processing greater than a terabyte of data, massively parallel, so hundreds, thousands of CPUs, and it must be easy to use. High-level applications written in MapReduce, programmers don't need to worry about sockets, hyperthreading, anything like that. So there's a radical way out of sharing where the nodes talk to each other as little as possible, maybe even never. It's a shared nothing architecture. And the programmer should not be allowed to explicitly create statements that share communication between nodes. The data workload is spread throughout the machines in advance, and computation happens where the data is stored, locally. So locality. The master program divvies up tasks based on the location of the data. This means that you have map tasks running on the same machine as a physical file data, or at least on the same rack. Map task input are divided into 64 or 180 megabyte chunks. They're the same as blocks or file system chunks. You process components on a single file in parallel, giving you that massive parallelization of the MapReduce framework. So what about fault tolerance? Tasks are designed for independence. The master must be able to detect worker failures, and the master must re-execute tasks that fail while in progress. So if you decide to restart one task, it does not require communication with other tasks. Data is replicated to increase availability, durability, and consistency. So what about optimizations? Well, Reducer can't start until the map is complete, so a single slow disk controller can rate limit the whole process. So you need to be able to fail a map task and start on another node if something's hanging. And the master redundantly executes slow-moving tasks and uses results to copy a finish. So some of the conclusions. Computing with big data sets is fundamentally a different challenge than doing big compute over small data sets. It's a new way of thinking about problems. New tools need to be provided. This means MapReduce, HDFS, hence the Hadoop stack. So thank you very much. If you have any questions, visit cloudera.com. You can find us on Twitter or Facebook, or give us a shout. Thank you.